All right, so it's unsupervised or self-supervised. And then conditional here in this case, as I said, I like to use the word conditioning when we do have, graphs, but when we do have target outputs. But yeah, so here in this case, we have supervised generative GNNs, and we're gonna look at conditional generation on graphs in this simple example. So here, what we have actually, we have two different examples. So first, you guys can take a minute to look at this and think about what is actually happening. Let's do that. So we have a source graph. So this is the input source graph. Okay, and we have a target graph. So from this particular source, there is parity here. So given the source, we want to predict a target. So that's why it's supervised. So these are in correspondence. These are kind of, paired or in correspondence here in this example. So the goal is to do a node edge code transformation. So this is the next, okay, node edge code transformation. And it's actually very simple. So using what we had done before, instead of reconstructing, so you have the GS, you move to Z. So, and then from Z, we reconstruct the GS. And now we're gonna do something else. So we have basically GS, Z, and G target, okay? So in this case, the first example is very important. So the first, this is self-supervised. Also, we call it unsupervised. It's self-encoding or self-generation sometimes, call it, or reconstruction. And the second one is supervised, because we encode the source graph into the Z here, and we decode it into something different, into a different target graph. Okay, so encode, decode, encode, decode. All right, two different scenarios. So far, previously, we have seen this scenario in these two examples, in the MLP-based one-shot and in the message passing-based one-shot. And now we're gonna see the conditional generation on graphs. So yeah, so this is actually very simple. All you need to do is to manipulate the loss. So the loss function here, if we write it in linear algebra, so if we have a target, right, and you want to minimize the tilde, the prediction by the network, what I predict by the network, and the ground truth. So this is the ground truth, and this is my prediction, prediction PR. Okay, so you want to minimize this kind of loss, and if you want to also do the features, we're gonna add, plus a lambda, and you do the feature matrix of target minus the predicted feature of target, as we have seen in at the very beginning of this lecture, and you can use different distances here. Okay, so all right, so this is just an example. And in B, we do what we call editing based next. So you do edit the graph. So by editing the graph, you take the source graph and you have the target. So you do some editing and using, of course, GCN, node embedding update, and you edit based on these embeddings. So you can think about how to do the editing, right? How to remove an edge. For example, here, this edge has been removed here, so it doesn't exist anymore. And how to add an edge, right? So for example, you can see that we added this edge right here. So this edge has been added right here. So editing, graph editing, it means you add an edge, add and remove edges, but not only edges. You can see that here we can do also, we can add and remove nodes, right? Remove edges / nodes, so end nodes. So this process of editing, right, of node edge editing is important because it allows us to gradually learn how to transform graphs. So these are a bit different. This is a different formalization from using the encoder-decoder networks. So here we learn how to operate on the graph, and we learn the transformation process. So we learn the transformation. So that's a co-transformation, actually. It's co-transformation because it's for both edges and nodes process. And it would be interesting to read these papers. For example, this paper right here, it uses the first paradigm, A, which is an encoder-decoder network. So it's a DAG-to-DAG translation network. DAG is DAG, so it's a directed acyclic graph, okay? And it means that the graph can be directed. So we have a node that, with different weights, for example, we may have something like this. Okay, so this is a directed graph, and it doesn't have a cycle. It means we don't have a cycle like this in the graph. Okay, so closed kind of cycles. So here in this example, what we have first, so let's look at this figure. So what is this graph translation about? First, we start with the input. So what are our inputs and outputs? The input graph is this one. So this is our input graph, has initial features, and this is our output graph. All right, so we want to learn how to generate this graph from this input graph. So first we do an encoder. We use an encoder network, a graph encoder. So you can easily encode the graph using like the methods that we have seen before. So you do a graph encoding or embedding. So we get the HG here. And after that, basically, you pass this onto a decoder. So you encode the graph, the whole graph. Look, guys, very simple. So it's also good to remember this. So this is a graph, for example. This is G. I encode it. So when we encode a graph, when we do graph-based classification, we have all these ping embeddings that we had before, right? So all these embeddings. Now what we're going to do, we're going to create we're going to collapse the whole graph onto a single embedding, which is almost one node, right? So this is one node. This is what we have here, okay? So this is HG of the whole graph. So we can use different types of poolings, and we learned about different types of poolings to do graph pooling, okay? And transform, graph embeddings across different nodes into a single embedding. So that's what we do. And here, we can use this later on we can pass this through a decoder. So what happens is that we're going to pass this entity here, the graph, basically the encoded graph into a single node and decode it into a full graph. So we do the decoding process depending on the number of nodes. So we have n modules. So n decoding steps. So every time we're going to add a node and connect it to the previous one and update the embedding of that node. So sequentially. So here until we get to the final node right here. So here we need n steps because the final graph has n nodes. So if we have, for example, 100 nodes, we need the model will have 100 steps. Okay, so in every single step, in each step, we will generate a node. Okay, cool. So according to some rules, and if you guys are interested in learning about how are we actually generating, how are we actually creating this direction right here, how are we updating the embeddings of this node and creating this third node right here, right, and then a fourth node over there. So how are we doing this until we get to the final node? And so you can read the paper, and it's also in the reference. But before you read the paper, I really encourage you guys to think about this problem. So think about these problems. Take pen and paper, scribble, use the lecture notes, what we have learned before, and try to formalize it mathematically. Try to kind of use the update rules, define, should I predict the node embeddings first, and then get the link based on the dot product, or maybe, there are different ways of doing this, and you can mix different strategies, but it's important to justify the logic behind your design and your intuition.